Hello, this is Arkasha from MCAT Simplified. Welcome to our video about isoelectric points of amino acids with ionizable side chains. So recall that every amino acid is able to exist as a Zwitter ion. So a form when it has both positive charges, negative charges, but overall the species is neutral. So they all cancel out. And for neutral amino acids, such as like glycine or serine or something like that, that don't have side chains that can ionize and act as, acids, bases, take protons, remove protons, and give protons, they only have two pKa values that are relevant for calculating the isoelectric point, right? They only have two groups that can ionize, and they are both found in the amino acid backbone. So that would include the amino group that is linked to the alpha carbon, and then the carboxyl group that is linked to the alpha carbon as well. And we would always call those, the pKa's, pKa1, which would refer to the pKa of the carboxyl group, and then pKa2, which would refer to the pKa of the amino group, okay? And generally speaking, right, the pi for any neutral amino acid, the isoelectric point, would just be calculated as the average of those two pKa's. pKa1 plus pKa2 divided by 2, you're averaging those, and that would give you the pi, okay? However, if you have an amino acid such as aspartic acid or lysine or arginine that also has a third ionizable group in its side chain, be it an amino group or a carboxyl group, or in the case of histidine, that imidazole ring, which has also an ionizable group, then that complicates matters, because then the pH at which the species is neutral overall, or the majority of the species is neutral overall, is going to be different. It's going to be affected by that third group. And so we're going to now identify a third pKa value, which we'll call pKa3, which is always going to refer to the pKa of the ionizable side chain. So pKa1 is still always going to be the backbone carboxyl group pKa. pKa2 is always going to be the backbone amino group pKa. But then pKa3 will be whatever the pKa is of the ionizable side chain, whatever that may be, okay? Now, again, the pKa values we're going to use are just estimates. They're not exact, okay? And typically speaking, if you have a question on your biochem exam or the MCAT, you should be given a table, or you're given those pKa values, okay? They're not exact, the ones we're using, all right? But these are good estimates. And the most important thing is that the process for determining what the isoelectric point is and titrating these amino acids to determine that is going to be the same regardless of what those exact numbers are. And I think that the best way to illustrate this is to go through examples, and we'll do aspartic acid, which is, remember, the one-letter abbreviation is D, and then we're going to do lysine, K, right, to demonstrate two different, essentially, scenarios where one of the ionizable side chains with aspartic acid has a low pKa. It's going to be negatively charged when it's deprotonated. And then for lysine, conversely, it's going to have a much higher pKa, okay? And we'll see that. So let's start with aspartic acid. So again, really the best way to approach problems like this is going to be to set the pH to 0. So imagine you're doing a titration, you have the amino acid in a solution, aqueous solution, and the pH of that solution is very low, it's 0, okay? And remember the golden rule, right, is that if the pKa of the group, okay, if the pKa is greater than the pH of the solution, that group will be protonated. And then conversely, if the pKa is less than the pH, then it's going to be deprotonated. And then when the pKa is equal to the pH, then you're going to have, for that specific group, half of the species in that solution are going to be protonated and half are going to be deprotonated. All right, so we're going to apply those rules to understand what's happening here and identify the pH at which you have the neutral species predominating, aka the isoelectric point. So again, we're going to have aspartic acid, which has the side chain of the CH2, the methylene group, plus then a carboxyl group. And we're going to start at a pH of 0, all right? And so at a pH of 0, we have the amino group is protonated, of course, because its pKa, we're going to say, is around 10. And then we know that these two groups will also be protonated, and so the backbone carboxyl group, which is, again, it has a pKa of pKa1 all the time, it's going to be around 2. And then we're going to say that the pKa3, the side chain pKa for aspartic acid, is going to be around 4. But again, this isn't an exact value. We're just estimating here. But again, the principle is going to be the same regardless of what that value actually is. All right. So this pKa3 corresponds to this group here. So at a pH of 0, because the pKa of all three groups are greater than the pH of the solution currently, they're all protonated. And so overall, this species at pH of 0 has a +1 charge, right? But then we're going to increase the pH. So we're adding base, right? We're adding base and we're increasing the pH. And eventually, let's say we look at a pH, we look at the species at pH of 3. So in this case, again, the amino group, the pKa is much higher than pH of 3. It's 10. So it's going to be protonated. So it's still positively charged, right? But then this carboxyl group, its pKa is 2. So in this case, most of it is actually now going to be deprotonated. But then the side chain pKa is still higher. It's pKa of 4. It's greater than 3. So it's still going to be mostly in the protonated state. So this one at a pH of 3, most of the species, or, at least here, is going to be neutrally charged, okay? Now, this isn't exactly the PI, all right? But we're just seeing that under a pH of 3, we're going to have a lot of the Zwitterion ion form, okay? Now, if we increase the pH further, so pH of 5, so now the pH is greater than the side chain pKa. So now both the side chain and the carboxyl group of the alpha carbon are deprotonated. And then, of course, the amino group is still protonated. So overall, now the net charge is -1, all right? And then finally, and so that's going to correspond to this part of the curve here, okay, it's going to correspond to kind of this part of the curve over here where the pH is going to be a little bit higher, all right? Now, finally, then if we increase the pH even further to a very basic pH of 12, that's going to be now higher than all the pKa's. So all the groups are deprotonated, including this amino group, and now the net charge is -2. So we're going to be somewhere over here on this curve, okay? But let's analyze this curve a little bit more closely. So again, we're starting at 0, okay? We're increasing the pH, and initially it increases pretty rapidly, but then we get to this first sort of buffer zone, right? Where we have some of the carboxyl group of the backbone protonated and some of it deprotonated. So we have kind of this conjugate acid, conjugate base region, right? Or both forms of it here. So it creates a buffer zone. And notice that when the pH is equal to pKa1, remember, that means that you're going to have about basically half of the species, in this case, this carboxyl group is going to be deprotonated, and half of the amino acids is going to exist in a protonated form. So that's when pH is equal to pKa1, all right? So that's the first buffer zone. And then eventually, if you continue to add base, you're increasing the pH, you're deprotonating pretty much all of this group. And then the pH suddenly starts to rise a little bit, okay? And it rises rapidly here in this region, but then it goes into another buffer zone. And that's because you have now this side chain, which starts getting deprotonated, okay? As the pH begins to increase over its pKa. And you get the second buffer region. And here, notice that when the pH is equal to pKa3, the side chain pKa, again, that means that exactly half of the amino acid in the solution has a protonated side chain and exactly half of it has a deprotonated side chain, all right? So that, and then notice this, that the average, so between these two is actually where the pH is equal to the PI, okay? That's where you're going to have this species predominating, okay? And as it turns out, the way that you would calculate the PI here is you would simply take pKa1, right, which is the carboxyl pKa of the backbone, plus pKa3, which is the side chain pKa, because those are the ones that exist on either side of this PI region here, and you average them, you divide by 2, and that's going to give you the PI, okay? So that's going to be, so for these numbers specifically, the PI is actually going to be 3. But again, in real life, these numbers are not exactly 2 and 4, all right? So the PI in real life would actually be slightly different for aspartic acid. In this example, it's going to be 3. When you plug 4 plus 2 is 6 divided by 2 is equal to 3. All right, and then at this pH, right, at a pH of equal to 10, for our example, that's equal to pKa2. So in this instance, you're going to have exactly equal amounts of amino acid with a protonated amino group and exactly equal to the deprotonated form. So the concentrations are equal. And then you have this third buffer region, okay? So that's going to be the case both for, basically for any acidic quote-unquote amino acid, like aspartic acid or glutamic acid, right? It's going to be the same principle, and the curve of the titration of those two amino acids is going to look the same. And in both instances, for both aspartic acid and glutamic acid, to calculate their respective PIs, you're simply going to take the pKa of the backbone carboxyl group and average that with the pKa of the side chain carboxyl group. All right, pKa1 plus pKa3 divided by 2 is going to give you the PI. All right. Next, we're going to take a look at the situation with a basic amino acid like lysine. All right. So for lysine, what we're going to say is that, again, we're going to use the same values for the backbone pKa. So pKa1 is going to be 2 for this carboxyl group. And then pKa2 for the amino group is also going to be 10 in this instance, okay? But then pKa3, because it now has an amino group as its side chain, this can be protonated and deprotonated. The pKa3 for lysine is going to be, we're going to say, around 12. Again, these are not exact values, but for the sake of this example, that's what we'll use, all right? So again, we're going to start at a very low pH of 0, and we're going to titrate up. So again, at a pH of 0, the pKa's of all three ionizable groups in the amino acid are greater than the pH, so they're all protonated. And so the net charge now, because you have two positively charged groups, is going to be +2. Subsequently, if we increase the pH to, let's say, pH of 4, where it now becomes greater than the pK of this carboxyl group, it gets deprotonated, and now the net charge is +1, since these two groups, of course, remain protonated, since their pKa's are still higher than the pH of 4. However, let's say we then increase the pH much more, right? We increase it to now above the pKa of the backbone amino group. So it's pH of 11, which is greater than 10. So then this group gets deprotonated, okay? And then we only have a negative charge and a positive charge. So this is a Zwitterion form where the net charge is 0, all right? And then lastly, if we continue to increase the pH, we'll eventually deprotonate the side chain too, which has a pKa, remember we're saying, of 12. So it's now deprotonated since the pH has increased above its pKa. And now the net charge is -1, since only the carboxyl group has a negative charge, or is charged at all, rather. And if we look at the curve is going to be different from the curve for aspartic acid, right? Because now, initially, you have this increase in pH, and then eventually you get to the buffer region corresponding to the protonated and deprotonated form of the backbone carboxyl group, right? So pH is equal to pKa1. That's going to be when you have exactly equal amounts of protonated carboxyl group and deprotonated carboxyl group. But then after that, you continue to add base, you get this very rapid rise until you get to the second buffer region, which now corresponds to basically when you have exactly equal amounts of protonated amino backbone group and deprotonated amino backbone group, all right? So at that point, the pH is equal to pKa2. Okay, and then you continue to add base, and you're going to get this initial rapid rise, but very quickly you enter a second buffer region, which is when you're going to have some deprotonated form of this and some protonated form of this, okay? Conjugate acid, conjugate base. And the when the pH is equal to pKa of 3, that's going to be essentially when you're going to have that third buffer region, or rather, that's going to be when exactly equal amounts of the side chain are protonated and deprotonated, okay? And here, notice that the PI is, again, it's the same principle. It's going to be the average of the pKa's on either side of this inflection point here. So it's going to be, again, pKa1, or rather, excuse me, in this case, it'll be pKa2, remember, because we're saying pKa2 is going to be the backbone amino pKa, okay, plus pKa3, which is always a side chain pKa, divided by 2, all right? And then that's going to give us the PI, which, using these numbers, because again, pKa2 is going to be 10, pKa3 is going to be 12, we said, using those numbers, 10 plus 12 is equal to 22 divided by 2 is going to be 11. So the PI, using these numbers, is going to be equal to 11. That's when the Zwitterion form is going to be the most dominant form. And again, this exact concept, this exact process is going to apply for all basic amino acids like lysine, and like arginine. Okay, so use that approach for those. All right, and that's it for our video on isoelectric points of ionizable amino acids. Check out our website at mcatsimplified.com.